Okay, we're going to continue on here. Still chapter 14, the big chapter of the season here. And we were talking about obviously acids and bases in this chapter to begin with. We got into weak acid problems and weak base problems. So remember that if we are looking to find the pH of either a weak acid or a weak base, it is going to be an equilibrium problem. You do need to do an ice table. We want to make sure we use our Ka value when we're dealing with anything that is a weak acid. We want to make sure we use our Kb value here for anything that obviously is a weak base. Once again, we could recognize when we should use those when we write the equation. If we have H3O plus on the product side, RH plus, it probably should be a Ka value that you're using. If you got OH minus there on the product side, you should be using really a Kb value. We do an ice table for both of these things. And really, when we do solve for X, in the case of a weak acid, that would be your H plus concentration, which means you could go into the pH equation. When you do the weak base, when you solve for X, that will be your hydroxide concentration, which means you do need to first go POH and then into the pH on that sort of move when you're doing the ice table. Again, you can make assumptions like normal. If it works, you should make sure you also check it to make sure it's okay. We also talked about, and we'll talk about more today here, is the idea that sometimes you are given the incorrect sort of K value that you need. Sometimes you'll be given a Ka value when you need a Kb value to do the calculation, and vice versa. So we saw a relationship that if you take the Ka times the Kb, that will equal Kw, which is 1 times 10 to the minus 14. So that is a really convenient way to convert from obviously Ka to Kb or Kb to Ka if you have those values and you need the opposite one. Once again, looking at your equation that you write correctly can again help you decide which one that you should be using in that particular situation. I think we also talked about percent hydrolysis, percent ionization. And percent ionization is the concentration of the H plus divided by the concentration of the initial acid times 100%. This is basically the way that we check our assumptions when we do make the X equals 0 assumption. Is basically that calculation. This also gives you, again, that percent ionization. And you could also use it for bases as well, based on how much hydroxide comes off versus how much H plus comes off in that particular case. We finished up talking about acid strength. And really, there's a few different things that we look at depending on the acid. If there's no oxygen in your acid, then you look at bond energy or bond enthalpy. And the stronger the bond energy, the weaker the acid is. And that's because it's going to be a lot harder to release that H plus because it takes more energy to do so. If you have an acid that does have oxygen in it, you look at one of two things, depending on the situation. You either look at the electronegativity of the central atom, or you look at the oxidation state or number of the central atom. In this case, if you did have two central atoms where they had really the same oxidation number, then you would look at electronegativity as being the overwhelming force there. And the one with the higher electronegativity would be the stronger acid because it will weaken that OH bond and allow that hydrogen to come off easier. Those with the lower electronegativity won't pull that polar bond as much, and it'll be a little bit harder to pull off that hydrogen. In a case where you have basically the same element, which means they all both would have obviously the same electronegativity, you would look at oxidation number. And it works the same way. The higher the oxidation number, the more positive the oxidation number, the stronger the acid would be. Again, for the same reason, it's going to really pull those electrons in from that OH bond, going to make it a lot easier for that H plus to come off, and make it a much stronger acid in that case. Any questions on any of that stuff there? Yeah. Yeah, so like the ones we looked at the other day, like HF, HCl, and so forth going through here. If you look at the bond energy between, say, these two guys, HF has a much higher bond energy than HCl. And because of that, it takes a lot more energy to break that HF bond than it does to break, say, the HCl bond. So much so that HF is considered a weak acid because it has a much higher bond energy than HCl, which has a lower bond energy, and it makes it easier for that H to come off. If you continue down that column there in group 7, HI has the least bond energy, and that actually means HI is actually the strongest of the acids there in group 7, even though HCl is usually the one most people talk about, but HBr and HI is actually stronger because it has a much weaker bond energy, allowing that H plus to come off a lot easier, making it obviously producing H plus a lot easier in solution. Other questions? Okay, then I believe where we laid up there is about salts. So what we're going to talk about right now is really one of the two things that is formed as a result really of a reaction with an acid and a base. So as you should know, when you take an acid and you react it with a base, especially a strong acid, strong base, but either way, an acid and a base, basically you get two things. You get water and you get a salt. And a salt, or a salt there. A salt is an ionic compound as a result of it. And once again, really the water is going to come from the H plus and the OH minus here in the base. And these two guys are going to come together to make our water. And really the other part here, I'll just call it A plus in this case, these two guys will come together to make our salt. So for example, if we had hydrochloric acid plus some sodium hydroxide, it really is a double displacement reaction, is where acid and base reactions fall under. They fall under the umbrella of double displacement because this is a positive, negative, which means we're going to get this switch that's going to occur here. Again, that's going to make our water. And in this case, we will make a little sodium chloride in this case. And this obviously would be our water and our salt in this particular case. In most cases, the salt is a soluble type of salt, which means it's a solution everybody's floating around. Now, the issue here is in the cases of the salts that are being formed, they actually can affect the pH of a solution depending on sort of where they come from. And what can happen is we could get a reaction that could occur between the salt and water, because frankly, that's the other thing that is present at that point in the reaction. And this type of reaction is sometimes referred to as a hydrolysis reaction, which basically means it involves water. And the result of this reaction form H3O plus. In other cases, it may form some hydroxide. And in some cases, frankly, it won't do much there in that case in terms of the pH. So what we're talking about now is really the salts and how they go about sort of reacting. And there are, as we'll see here, neutral salts, acidic salts, and basic salts that can be formed. So let's first take a look at neutral salt solutions. So basically any salts that contain metals from the alkali metals or the alkaline earth metals, basically group 1 or group 2 on the periodic table, will result in a neutral salt. So there's a relationship that we talked about earlier on in this chapter in terms of an acid and its conjugate pair and a base and its conjugate partner. And just to remind everybody here, if I have a strong acid, its conjugate base will be strong or weak? It will be weak. It's basically an opposite sort of relationship. If you have a strong base, its conjugate partner, which is this conjugate acid, will also be weak. So it's kind of opposite of where it comes from. If you have something that came from a weak acid, its conjugate base would be relatively strong. And if you had a weak base, its conjugate partner there, which would be the conjugate acid, would also be relatively strong. So this opposite relationship that we talked about, I think when we talked about sort of Bronsted-Lowry acid-base pairs, is really important for salts. So if you think about where the salt comes from, you could think about whether or not what you have there is going to be relatively strong or not. In the case of salts and hydrolysis reactions, if it is sort of a strong partner that is there in the salt, it will then react with water, basically. If it comes from anything that is a strong acid or a strong base, the salt part there is relatively weak, which means it will not continue on and react with basically water in this case. So that is sort of the two things that we're going to think about here as we talk about these salts. So when we have a salt that contains really a alkali metal or alkaline earth metal, R comes from a strong acid, R base. It is going to be basically what is considered a neutral salt. And it would have a pH of 7, which is neutral in that case. So why are we talking about alkali metals, alkaline earth metals? As we talked about, that is group 1 and 2 on the periodic table. And group 1 and 2 on the periodic table typically have strong bases is where they come from, right? Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. So really, that's why we say anybody from group 1 and 2 is going to be neutral, because frankly, they come from something like sodium hydroxide, potassium hydroxide, which is a strong base, which means they're going to be relatively weak and not go through hydrolysis. Anything that comes from something like a strong acid will also be relatively weak. So if we think about this salt right here, which is sodium chloride, if we think about it backwards, it is pretty much that reaction I just wrote on the previous slide. It most likely came from hydrochloric acid plus some sodium hydroxide. And that would get me water plus my salt here. So the Cl minus part, which is this guy, really came from HCl. So HCl is a strong acid, Cl minus is this conjugate base, and because HCl is a strong acid, the Cl minus is going to be relatively weak, which means it's not going to react with water, it's going to be neutral. The sodium part of this really came from something like sodium hydroxide, and once again, sodium hydroxide is a strong base, which means the sodium part there, the sodium ion, is going to be relatively weak and neutral as well, and really is not going to react. And we would expect basically, again, the pH here to be 7 or neutral. So if you come across a salt, sometimes it's kind of important to think about sort of where it came from, how that salt was sort of derived. And again, if you find that that salt most likely came from both a strong acid and a strong base, pretty much that's going to be a neutral salt. And again, if you were to check the pH, you would anticipate it to be more of a pH of 7. Any questions on neutral salts? But now if I took, say, a different acid, something like acetic acid, which is a weak acid, and I react it with sodium hydroxide, which is a strong base. What we're going to end up with is, again, water made from the H plus from the acid, the OH minus from the base, and a salt, which is going to be sodium acetate in this case. So we have our water and our salt in this case. Now, when we look at sort of what we're left with at this point, we are left with basically water and a salt as a result of this reaction. And we would want to look at this salt. Now, this salt is a strong electrolyte, which means when it is in solution, it is going to basically break apart into sodium ions floating around and some acetate ions floating around. So when we look at this particular salt, what we want to analyze is there any part of this salt that will basically continue to react with water and go through hydrolysis? So again, thinking about where it came from, we know that sodium, which is group 1 on the periodic table, and pretty much came from this strong base. We know that it is going to be a neutral salt and not go through hydrolysis, as we just talked about a second ago. When we look at acetate in this case, it came from this guy, basically. And that is a weak acid, which means that the acetate will be relatively strong. And in the case of this, it will then react with water in this case. So this guy, because of where it came from, will actually react with water. Now, because it came from a weak acid, it is basically the conjugate base in this case. And that's really important when you think about how it's going to react with water, which, by the way, in case you're curious where the water comes from, right there, it's basically an aqueous solution. There's water in there. So what we're going to get in this case is it's actually the acetate part of this salt that will continue to react with water. And this is, again, what is referred to as a hydrolysis reaction. Now, in this particular case, because I know it is a conjugate base, that means how it reacts with water is it's going to react as a base. Definition of a base is something that will accept an H+. So what's going to happen in this case is it is going to take basically an H+ away from the water. The result of that is you will always form where it came from. If I could write the right letters there. So you will always form really where it came from. So in this case, when the acetate picks up the H+, it will make acetic acid. And when the water loses the H+, you are left with hydroxide. And that's because if you take an H off of water, you have HO. And if you take a plus off, it becomes one more negative, and that makes it OH- that's left over at that point. First off, any questions on that reaction that's going to happen here? And again, this reaction is going to take place because that acetate is relatively strong in the sense that it will react with water because it came from a weak acid. Now, without even doing a calculation at all, should this solution be acidic, basic, or neutral? What do you think based off the equation? It should be basic. I think I hear somebody whispering. So that is what it should be. And it should be basic in this case because it is producing hydroxide. So because the salt then continues to react with water, it will produce hydroxide. It will increase the hydroxide concentration in the solution, and it will be basic here. If I wanted to calculate the pH of this salt solution, I would need to do an ice table in this case. So I would do an ice table here with my molarity, some zeros, minus X's, plus X's along the way here. Molarity minus X, X, and X. This would go into my K expression, which would be my products over my reactants. And by the way, this should be a K, A, B, C, D, F, G. This should be a K. Which K value should I use here? It should be a KB once again, because I see hydroxide here on the product side. So this is why I say it's super important to make sure that you know how to properly write these equations. It could help you with the calculation part. This is also a situation where if you were given this problem, you might be given the Ka value instead of the Kb value. So this is the place, and it's definitely salts is the place where we oftentimes will use Ka times Kb equals that Kw relationship. So this is definitely the place where it comes out a lot, is when you're doing these sort of hydrolysis problems, these salt sort of problems. Obviously, in this case, we would solve for X, and we do want to remember that in this particular case, X is actually the hydroxide concentration. That means that you do need to kind of go a POH route first, probably, and then to the pH at that point. So this type of salt, where it really comes from a weak acid, and it really comes from a reaction of a weak acid with a strong base, the salt itself, one part of the salt will go through hydrolysis, and that salt will always produce hydroxide. And it means you always need a Kb value, get the POH and then to the pH. Any questions on that there? Yeah. So the sodium ion is what we were just talking about a second ago with neutral salts. And it's because really the sodium ion comes from a strong base. And really a strong base or a strong acid, its partner, which in this case would be the sodium on this side, its partner is going to be really relatively weak, which means it will not go through hydrolysis. And that means it's considered really a neutral salt, that part of it, the sodium part of it. So it will not do anything. It won't react with water. And that's really why the previous slide we were looking at, where it says anybody really from group 1 or 2 on the periodic table is a neutral salt, because again, that's pretty much where our strong bases come from, group 1 or 2 on the periodic table. And that would mean that their partners would be relatively weak. The conjugate base of a weak acid would be relatively strong. And in the case of what we talk about relatively strong, it's not as strong as, say, a strong base. So this base here, the acetate, for example, is not as strong as, say, sodium hydroxide. But it is strong in the sense that it will continue to react with something like water and produce hydroxide. So that's sort of the relationship. If you have those two things together, which we'll come across that when we talk about titrations, if you have those two guys there, like sodium hydroxide there and acetate there, they both will act as bases. But even though they're both technically kind of strongish, really sodium hydroxide is a way stronger base, because sodium hydroxide just simply needs to go for a swim and it's going to produce hydroxide. It's going to break apart and produce hydroxide. Acetate's got to go find some water, do a little bit of a reaction. It's a equilibrium type of thing, which means it's not going to produce nowhere near the extent of hydroxide that sodium hydroxide would be. But in this application, it's considered strong because it's able to continue to react with water. Other questions? So that's what we were just looking at there. And really any salt that really does come from a weak acid will go through hydrolysis. And again, it will always produce hydroxide. And again, if you do a calculation, got to have that Kb value in that case. Now, let's talk about acidic salts and sort of what happens with acidic salts. And we can get acidic salts through a reaction of actually a weak base with a strong acid. So if I took a weak base, something like ammonia, which is a weak base, and I react it with something like hydrochloric acid, which is a strong acid, I think still. The result of this is we're going to end up with really a salt of ammonium chloride. And you can keep it together, or if you want, you can break it apart. You get ammonium and chloride ion, basically. And that's because this is going to send the H plus over, basically. Yeah. So when we look at that salt of ammonium chloride, I just wrote underneath it what it breaks apart in. But when it's now in solution and it's been created, it is not going to stay together again because it's a strong electrolyte. So it will break apart into NH4 plus and Cl minus. So once again, when we sort of analyze this salt, we want to look at the two parts of it and determine, is there any part of it that will basically go through hydrolysis, will continue to react with water? So we'll start with the Cl minus. Once again here, the Cl minus came from, if we think about it sort of backwards, is it came from a strong acid. That means that Cl minus should actually be neutral, right, and relatively weak. So this guy is not going to have any effect on the pH because it's really a neutral salt because it comes from that strong acid. When we look at the NH4 plus in this case, it comes from a weak base, which means the NH4 plus should be relatively strong, right? And the result of that is it should go through hydrolysis. So this guy will react with water because it comes from a weak base, which means it's relatively strong and will go through that hydrolysis reaction. Once again, we do know that it comes from a weak base, which means basically this is the conjugate acid. And again, that's really helpful for you to write the reaction that's going to take place. So when I take my NH4 plus, which I know will go through hydrolysis, and I react it with water, I know that the NH4 plus here is going to act as an acid. And the definition of it as an acid is it's going to donate the H plus over. When it donates the H plus over, once again, it will always make where it came from. So it will make some NH3, just like in the previous example, the acetate made acetic acid. So a lot of times what you will have in a problem is, frankly, the entire equation almost given to you, because if you know where it came from, that's going to be on one side of the arrow, and what you're dealing with will be on the other side of the arrow. When the water gains the H plus, you will get H3O plus being made in this case. So once again, just strictly looking at the equation that we have up there, we would expect the solution to be acidic, basic, or neutral. This one should be acidic as we are producing H3O plus. Even if before you do the calculation, you can make a pretty safe bet that when you do the calculation, you should end up with something that's acidic here. To do this calculation, much like the last one, it will require an ice table to do so, and it would be molarities and zeros and X's and all that good stuff, right? This would obviously go into our K expression, which once again, in this example, would be our products divided by our reactants. And you're going to tell me this is going to be a Ka, B, C. Which one? It should be a Ka, also because we see H3O plus there on the product side. So a little bit different in this one. When you do solve for X, and by the way, you could do all your normal stuff, make an assumption, whatever you want to do to solve for it. It actually will equal the H plus concentration, which means you could go right into the pH. So when we do have a salt that basically originated from a weak base, it will go through hydrolysis, it will react with water, and when it reacts with water, it will react with water as an acid, and it will always produce H3O plus in solution, which means you always should end up with something that's an acidic solution at that point. And again, you should be using the Ka value if you were going to calculate it. Question on acidic sort of salts. Now, there is also another sort of way that we could get acidic salts to sort of happen. And we'll take a look at that on the slide here, I think. Another way that an acidic salt can kind of happen is actually when we have a metal. So if we have sort of a small metal that has a pretty good positive charge, +3s or more, 2 or 3s. And a lot of times those are going to be your transition metals can do this. They will actually go through hydrolysis and will basically surrounded by 6 waters. That's essentially what aluminum is. When we put aqueous next to it, there's basically 6 waters. So basically what we have in the case of aluminum is we have this aluminum with a +3 charge. And we got basically 6 waters attached to it. So I'm not going to draw out all the waters. I'll just write them like this. By the way, they are attached through the oxygen in each of these cases, as oxygen is more negative, right? Aluminum is positive. So that is where the connection happens. And I will 1, 2, 3, 4, 5. I'll draw out one of the waters that looks something like this that's attached. By the way, the overall charge here on this is a complex ion. Overall charge is +3 because water is neutral and aluminum has a +3 charge. So what happens in this situation is you basically have this positively charged metal in the middle. You have all these guys that are attached like water, which are referred to as ligands. We'll talk about in a later chapter. And it creates this complex ion. And essentially what happens is another water, minded in its own business maybe, will basically take a hydrogen off of one of the waters that's attached to the aluminum. The result of that is we will now make H3O plus here, which is the hydronium ion, which is why it is basic, acidic in this case, right? What happens to our sort of complex ion is, frankly, if you look at it, there's still 1, 2, 3, 4, 5 waters that are intact, which is why this says H2O to the 5th, right? There's 5 waters that are basically still there. One of the waters will lose that H plus, and that's why there's an OH here. That's the one that lost the H plus that came off. And when it loses an H plus, it becomes one more negative. So that's why the overall charge here drops to +2 from +3. It's that H plus that basically came off from that. So this is another way that basically you could have sort of an acidic salt. It's sort of again, a lot of times it'll be sort of a transition metal there that has a pretty good positive charge and some type of ligand like water attached to it will do that in that particular case. Questions on that there? So there really is 3 types of salts. There are neutral salts, and really neutral salts, you want to think about salts because in a lot of cases you'll just be given the formula of a salt, and you want to think about where it comes from. And if it does come from a strong acid or strong base, pretty much that salt's going to be neutral. If it comes from a weak acid and a strong base, because of the weak acid, that salt will go through hydrolysis and produce hydroxide and be basic. And if it comes from a weak base and a strong acid, because of the weak base, the salt will go through hydrolysis and produce H3O plus and will be acidic. Along with that, some of these metals. Any questions on the reactions of salts here? All right, let's take a look at some here. Take a second here or so and predict what the pH of a 0.45 molar potassium chloride solution would be. All right, let's take a look at this here. So that's KCl, which is our salt. So really we want to think about this salt and what it will break apart into in solution. It is going to be K plus and Cl minus. So now what we want to think about is there any part of this that will go through hydrolysis? Is there any part of it that will go through hydrolysis? So let's first off then think about where it came from. So if you had to venture a guess as to what acid and base made KCl, what acid do you think made? Yeah. And the base that made the KCl would probably be KOH, yeah. And that would get you some water plus some KCl, right? So HCl, what type of acid? Strong, right? KOH, what type of base? Strong, yeah. So when we look at the salt that was made here, the K plus most likely came from a strong base. That means K plus going to be strong or weak? Weak. Also group 1 on the periodic table, which means that is basically neutral, right? The Cl minus came from a strong acid, which means the Cl minus is going to be strong or weak? Weak, which means it's going to be neutral, which means this is actually a neutral salt of a pH of 7, I suppose. So the pH here, no calculation needed in this case, should be a pH of 7, because really they both come from a strong acid and a strong base, which means neither one of them are going to continue to react with water and produce anything, and they would be neutral in that case. Any questions on that one there? All right, so again, this is why it's important to think about where these things came from so you understand how things might react. So let's do one where there is a calculation involved. This one you do need to do a calculation. All right. So let's say you have this salt here, a little sodium fluoride. It's a 0.3 molar solution. What is the pH if the Ka value for HF is 7.2 times 10 to the minus 4? So try to work through the calculations, see what you come up with, and then we will talk about it here. Okay, let's take a look, see how you're doing. So once again, obviously we have a salt here. And what we want to think about is when this salt breaks apart and it's really in solution, it is basically a sodium ion floating around and a fluoride ion. So we already want to think about will any part of it go through hydrolysis? And we've talked about the sodium before here, and that sodium is group 1, which means it's really from something like sodium hydroxide, and it is a neutral salt, which means it's not going to go through hydrolysis. What about F minus? Will it go through hydrolysis? It will, because it most likely came from, and the other thing that you do not want to overlook is the big hint that's right here. I have a Ka value for HF, which means HF is a weak acid, and that is most likely where this guy came from. It most likely came from the reaction of HF with a little sodium hydroxide. Going to produce some water and some sodium fluoride in this case, yeah. So again, a lot of times in problems, especially salt problems, you'll have these sort of hints given to you. You don't want to overlook it. It comes from HF, which is a weak acid, which means that this guy will be the conjugate base and will be relatively strong and go through hydrolysis. So now that we know that it will go through hydrolysis, it is going to react with the water that's hanging out there in the beaker or wherever it's at. It's going to do F minus plus some H2O. Once again, because I know it comes from a weak acid, it should act as a base when it reacts with water, and that means that it should accept the H plus in this case. By the way, also logic tells you it does not have an H to give, so it cannot give, right? So it can only accept in this case. The result of that is, by the way, in case you're not sure how to write the equation, it always will form where it came from. So it's going to form HF, which is usually given to you, like, for example, in this problem. And the result of this would be hydroxide being formed when water loses it. Without doing a calculation, we should already know that the answer should be acidic, basic, or neutral. Which one? Should be basic, because we got some hydroxide happening here. So we definitely should be basic. Good way to check your calculation at the end, just to make sure you didn't screw up somewhere or thought about something wrong. All right, so we're ready to do our ice table. So we're going to do our ice table here. And initially we have 0.3 molar. That comes from the sodium fluoride. Sodium fluoride's a 1-to-1 relationship, which means the concentration of sodium fluoride is 0.3. So would the concentration of F minus in this case. It would also be the concentration of sodium, but we don't need it. But it is 0.3. Rest of this is going to be zeros. Change is going to be minus X, plus X, and plus X, which means when we get down here, we got 0.3 minus X, X, and X. Any questions on the ICE table here or the reaction? All right, so this is going to go like normal into our equilibrium expression. So we got a K that is equal to our products over our reactants. And by the way, this should be a KB. Yes. Once again, here we got the hydroxide. And very commonly, though, what was given to us is a Ka value. So we do need to use that relationship that we talked about earlier, Ka times Kb equals Kw. So if we do that to get to the Kb here, it would be 1 times 10 to the minus 14, which is our Kw, divided by 7.2 times 10 to the minus 4. You do not want to use the Ka here, otherwise you will be wrong. And you will also be like a lot of students that use the Ka here. So make sure that you are using the Kb here. 7.2 to the minus 4, going to give us, looks like a 1.4 to the minus 11, we'll call it. All right, now that we have the right K value here, which is the Kb, that equals 1.4 times 10 to the minus 11. Putting in our equilibrium line, x squared over 0.3 minus x. We could assume that x is equal to 0 here, because that looks pretty small. That's going to give us x squared over 0.3 equals 1.4 times 10 to the minus 11. I'm going to multiply this to the other side and also take the square root of it. So when I do that, 1.4 to the minus 11 divided by 0.3, a little square root action on it. Going to give me, looks like an x value of 6.83 times 10 to the minus 6. We do want to check it, so we're going to divide that by 0.3, times it by 100. And our check is good. It's not even 0.1%. So the check is good here. So we also want to remember, and again, important to make sure we have written our ICE table correctly here. That X does not equal the H. That means that we would have our OH minus concentration in this case. All right, so that's going to give us to our POH here. And maybe I'll just go on the next page here. So we have our, yeah. I'm sorry? This part right here. I multiplied the 0.3 to the other side, and then I took the square root. Yeah, so you basically had here we had basically had x squared, right? 0.3 equals 1.4 times 10 to the minus 11. You had to multiply that to the other side, give you x squared equals 1.4 times 10 to the minus 11 times 0.3, right? Get rid of that, then you got to take the square root of both sides, yeah? Like the minus x, we assumed that x is equal to 0 because of the small value of k, yeah. Other questions on that? Okay, so we checked our assumption, and again, that's why we got rid of the x that we were subtracting from. it was a good assumption, and that meant that our OH minus concentration in this case was, I believe my X value was like 6.83 times 10 to the minus 6. That's going to get me to the POH, which is minus the log of 6.83 times 10 to the minus 6. That would equal like a 5.17. We then want to make sure that we do subtract the 14 there to actually get to the pH. And again, this is also why writing the equation, understanding that this should be basic, should make sense to you. In case you thought this was the pH, that would not be a correct number if you did think that was pH. That gets us like a 8.83, which is a basic pH, and should make sense to you based on the reaction that's occurring. Question on that one there. So there is usually a lot of sort of hints in the actual problem, and sometimes people do overlook it, and it can help you if you look at the problem, help you write the equation correctly and sort of understand what should be happening in it. So just don't overlook that information that's in there. Any questions on that there? All right, let's try another one here. Let's do what is the pH of a 0.75 sodium cyanide solution there? All right, let's take a look here. So once again, we do have the salt, which is our sodium cyanide. Again, in solution, it will break apart because it's a strong electrolyte into Na plus and Cn minus. Now we want to do our evaluation process here, and we've talked about sodium a bunch already. We know that we really don't have to worry about sodium as it's a neutral salt. Again, probably came from some type of strong base like sodium hydroxide. The Cn minus here, we have a pretty big hint of where it came from, which would be the HCN, and that has a Ka value, which tells me this is a weak acid, and that would mean that this would be its conjugate base. And because it is a weak acid, that Cn minus should be strong enough to go through hydrolysis and react with water. So that is where we should get our reaction from. It will be our Cn minus, which will then react with water. And once again here, it's going to react with water as a base, which means it's going to accept the H plus. And just like the last one, it really doesn't have an H to give. So we could feel pretty safe about that. Once again, it will always make where it came from. So we know on this side, it will make where it came from, which is the HCN. And the result of that, once again, here will produce hydroxide as it is coming from a weak acid. And just like before, we once again should know our answer should be basic because we are producing hydroxide. Any questions on that there? Now we'll roll into our ice table. So we'll do our 0.75, our zeros, minus X, plus X, plus X at this point. And through here, 0.75 minus X, X, and X. This will go into our K, which also should be a B value here because of the hydroxide. And that would be our HCN, our OH minus, and our Cn minus. Now to get that value, we do need to once again use our Kw equals Ka times Kb. So once again here, the Kb would be 1 times 10 to the minus 14, which is Kw, divided by our Ka that was given to us, 6.2 times 10 to the minus 10 in this case. Going to give us looks like a Kb value of 1.6 times 10 to the minus 5. So putting in our values there gives us x squared divided by 0.75 minus x equals 1.6 times 10 to the minus 5. Once again, here we're going to assume that x is equal to 0. That would get rid of this x right there. That would then reduce us down to x squared divided by 0.75 equals 1.6 times 10 to the minus 5. Once again, I'm going to multiply this to the other side and also take the square root of it. And if we do that times 0.75, a little square root action, that is not the square root. Try a different button. Try maybe that button. That works. There we go. All right. So if we take the square root of it, going to give us an x value of like 3.48 times 10 to the minus 3. Once again, we do want to check it, so we'll divide that by 0.75 times it by 100% just to make sure. You're usually pretty okay in these situations, and it looks like we still are. So the check is good here. From our ICE table, once again, that x value will equal our hydroxide concentration. That would allow us to calculate the POH as minus the log of 348 times 10 to the minus 3 and minus the log 3.48 to the minus 3. Going to give us a POH of 2.46. Remember again that is the POH, so we do want to get to our pH, and our pH here would then be 14 minus our 246. So minus 14 looks like an 1154 pH, which does make sense as that is obviously basic in this case. Yeah. Any questions on salts and hydrolysis here? We did a couple here with hydroxide, but again, if you had one that did form H3O plus, the only difference here is you would need to make sure you use a Ka value. And once you get the X value, you can actually go right into the pH equation because that is the H plus concentration. If you did have one that produced, obviously, H3O plus. Question on any part of that calculation there? Now, a couple other things about salts here. That's just a picture of the aluminum that I drew earlier. Much nicer picture. Only one part of the salt will go through hydrolysis, maybe the positive guy, maybe the negative guy. It is possible that you could have a salt where both parts of it actually went through hydrolysis. So for example, if you had a salt like NH4NO2, that is NH4 plus, which came from ammonia, which means it would go through hydrolysis. That is NO2 minus, which is nitrite, which came from nitrous acid, which means it would also go through hydrolysis as well. So in those situations, the calculations can be really complicated if both things are happening at once. So what we do in those situations is we compare the Ka value to the Kb value, and pretty much whichever one is larger is what type of calculation you would do. So if you compared the Kb to the Ka value, and the Kb was larger in this case, you would do it as a basic sort of solution. If you compare the Kb and it's less than the Ka value, you would do it as the Ka calculation and do it for acidic conditions. And if they're about the same, it would be neutral in that case. So in a situation, if you happen to have both parts of salts going through hydrolysis, you want to compare the correct Ka to the Kb values, the correct values for that. And then again, whichever one's larger, if the Ka is larger, just do a Ka type problem and an acid problem. And if the Kb is larger, you would do a Kb or a base type problem for it. If they're equal to each other, then it would be neutral. So here's a table. You have a similar one in your book that kind of explains what we just talked about. Again, our neutral salts, our basic salts, and our acidic sort of salts here, along with obviously what happens if we need to compare them. All right. Now, there are certain elements and oxides of those elements, and obviously oxides of elements means that they have oxygen. And there are certain ones that are sort of what is referred to as basic oxides, and there's some that are referred to as acidic oxides. Pretty much all these guys over here in the green, these are our basic oxides, which means pretty much if you react them with water, you'll get a base, like sodium hydroxide, potassium hydroxide, all those good things. All these kind of bluish guys over here, these are our acidic oxides, which means if you react it with water, you will get an acid. Like if you took water plus some CO2, that makes some carbonic acid. So that's an example of that. If you actually take the N2O5 there, a couple of them, and that's how you get sort of nitric acid will form as a result of that. These orange guys here are amphoteric oxides, and if you remember, amphoteric means can either be an acid or a base, right? That's basically what amphoteric means. So those are guys that can go kind of either way when they do react with water. Now, there are a few different definitions of acid and bases that we've come across up to this point. We talked about the Uranus definition of an acid and a base. Obviously, an acid is something that produces H plus or H3O plus, and a base is something that produces hydroxide. The Bronsted-Lowry definition, which is a really important definition in acid-base chemistry. An acid is a proton donor, right? And a base is a proton acceptor. And obviously a proton is H plus. But our good friend Lewis didn't want to be left out. And when we think about Lewis, we think about everybody's favorite thing, which is Lewis structures. And when you draw Lewis structures, they are involved what things? They involve, what are the dots on Lewis structures? Electrons. So Lewis's definition of acid and bases obviously involves electrons. A Lewis acid is a substance that will accept a pair of electrons, while a Lewis base is a substance that will donate a pair of electrons. Now, just because somebody has a pair of electrons doesn't necessarily mean it's able to donate them. Things that basically can donate electrons are things that are electron rich. So those are a lot of things with negative charges, right? The only way you become negative charge is you gained electrons, which means you gained electrons. That means you got some to give. Also, non-bonding electrons in polar molecules also are guys that can give away electrons. Lewis acids are typically things that are electron deficient. So things like with a positive charge, right? That means it's lost some electrons, it's electron deficient. That's like our aluminum there in the previous one where we had all the waters attached to it with the +3 charge. +3 means it's pretty deficient in electrons, so it would be the Lewis acid, and the Lewis base would actually be the water in all those cases. So if we look at sort of some definitions here or some examples, here we have H plus and OH minus. In this case, this is going to be our acid. Our Lewis acid is deficient in electrons, and the electrons are going to be transferred from our hydroxide here, which would be our Lewis base. This is H plus, which is deficient in electrons, which would be our acid. This is ammonia, which is a good Lewis base. It's a polar molecule that has non-bonding electrons on its nitrogen. Those electrons are going to come on over here and make this guy a base. By the way, both of these definitions of Lewis acid and Lewis base, they match up with Bronsted-Lowry acid and base in terms of they tell you the same thing, which one's the acid and which one's the base. In a Bronsted definition of acid and base, the H plus would be donated, which in this case, the H plus would be the acid. OH minus would accept the H plus. It would be the base. Same thing here. The H plus would be donated, and the NH3 would accept the H plus, which would make it the base. So although the definition is a little bit backwards in terms of Lewis acid and base, as in the Bronsted-Lowry, the acid donates the H plus, the base accepts the H plus. When we're talking about electrons, basically the opposite process that occurs, but they both give you the same definition of which thing is the acid and which one is the base based on it. The sort of usefulness of a Lewis acid and base is in a situation like this, there is no transfer of a proton. So because there's no transfer of a proton, You could still apply acid-base chemistry to this using Lewis's definition. Boron, as you might be familiar with, that is like our incomplete octet, right? It is less than 8 electrons. It is electron deficient, which means it wants to accept electrons. And that means that the BF3 would be our Lewis acid in this case. And the NH3, which has the pair of electrons to donate, would donate those over to the boron. And that would be our Lewis base in this case. So here you could apply, like I said, sort of acid-base chemistry in a situation where even an H plus is not involved. But you could still use, in a lot of cases, the Bronsted-Lowry definition of acid and base and still be able to figure out which one's an acid and base. We will definitely see Lewis acids and bases later on in the semester when we talk about transition metals, complex ions, and coordination chemistry. All of those interactions are pretty much Lewis acid and base interactions with electrons being sort of donated and accepted. And we'll definitely see them a lot more down the road here. Any questions on Lewis acid and bases? All right, so I think that's a good place to lay it up here for today.